In this day and age, we see containers coming up as a new way to deploy software. And that is because containers have, as a technology, have quite a few advantages over other ways of doing things. First, let's have a look at why we want to look at things like these. The ever-changing need is the need for speed. And that is to speed up the platform so that we can deploy our applications and our software faster and make it respond faster to the requirements that we have. Here's a slide from an otherwise pretty brilliant presentation by Adrian Cockcroft, who was a CTO at Netflix and is now a vice president at Amazon Web Services. And this slide he points out that we used to have these data center snowflake servers that could take months to deploy and then would live on for years. Now, about 10-20 years ago, we gradually moved to virtualization and cloud, where a virtual machine would deploy in minutes and would be alive for weeks, sometimes days, sometimes longer. And this is where containers are an evolution of, where especially Docker containers deploy in seconds and then live for minutes or hours. Now, beyond containers, we have stuff like serverless, like Amazon Lambda and Google Cloud Functions, which deploy in seconds, milliseconds, and will only live for like 30 to 60 seconds. But that's a completely different architectural style. And that is not always relevant for your application these days. But that's a different story. So why do we have these containers? Well, from the software development business perspective, this enables microservices that scale flexibly, and that has a number of benefits both in the development process as well in the runtime environment. There are also standardized runnable units that can be deployed across our environments, so from development to production, because it is a more portable execution environment, as I will point out in a little bit more detail later. Technically, there are some advantages. One of them is that a container has a much smaller memory footprint, as we will see in a second, allowing you to make more efficient use of the hardware. And related to that is the fact that they just boot much quicker than a virtual machine. Now, all of this is because of the way the technology works. So let's have a look at the difference between containers and virtual machines. If you look at the left, you'll see that there's this container running an application together with its libraries, running facilitated through a Docker daemon that then runs on a host operating system. So multiple containers share the same host operating system. By the way, the host itself can run either on virtual memory or on bare metal. On the right hand side, we see how virtual machines work. And there you can see that each virtual machine has its own copy of the guest operating system. Now, the benefit is that these guest operating systems can be different, and the disadvantage is that these guest operating systems, well, can be the same, and you're replicating all the files that are in there. So the memory footprint of that is a lot bigger. They do give much better isolation between guest operating systems. So that's an engineering trade-off in sort of. Containers are often used in a continuous integration or even a continuous deployment pipeline, where on the left-hand side you have a repository of source code and test sets. That is, when that's committed, a trigger will go to the build server, the CI server, that then creates the image and pushes it to a registry. Now, out of that registry, a host on the right-hand side pulls the container, as it's called, and runs that. Now, in reality, on the right-hand side, you're not running containers on a host, you're running them through an orchestrator on a set of hosts. And that story is in the next slide. Orchestration is really where the power of containers comes to life. The idea is that you have that your application has a bunch of containers, and maybe multiple applications have a bunch of containers, and the scheduler, the orchestrator, which operates on the right-hand side in this picture, allocates those containers over multiple pods, machines, groups, etc. There's a whole hierarchy of replication out there. What you also see if you look carefully is that the application containers, when they run on the same host, they share the same port address space, so the same networking port address space, and that's why they run on different ports in this story. Anyway, the most popular orchestrator these days is Kubernetes, which was originally developed by Google, but it's now open source, and it is also used by all the other major hyperscale cloud providers. And they have some bickering on who owns what, but for the purpose of our discussion, the Docker deployment is to a pretty much a standard environment. Now let's dive a little deeper into what containers and images are. So the container is the actual running unit. It's the process or the virtual machine. It's something between a process and a virtual machine, you might say. And if it implements a microservice, which means it has an API that it exposes, it probably runs a web server to listen to the API. Even if that API or that web server is not publicly facing. Now the Docker image is what this is kind of booted off from. It's like a traditional bootable image, but it's slightly different. And I'll talk about that in a second. Docker images contain ready-to-run pieces of software. It could be like a Linux kernel with an Apache web server on it. And here's a picture, an architectural diagram from the Docker website that explains that in a little bit more detail. And this is really the twist in the underlying technology. The idea is that these layers are layers of file systems that are read-only. So when you add the next piece on it, the next container on it, it only makes adds the files that are different from the underlying image. So there's like a differential file system, or officially it's called a union file system. And then you freeze them into an image, and then you can create another layer on top of that. And only the running image, the container, will have a writable file system. Now we're mentioning Linux as a technology here, but you can also have container technology on Windows. But that's a little bit beyond this presentation right now. And I don't think that the principles are much relevant for the discussion right now. Diving into some of the components of the ecosystem, let's get into the Docker daemon. How does this actually run? Well, the core thing is the Docker daemon that within a Docker host manipulates the containers and instantiates them, freezes them, and what have you. It's the sort of the thing that is confined to the specific machine or virtual machine that does the Docker thing in there. The orchestrator will actually talk to the Docker daemons through some kind of API. Now the Docker client in this picture is the thing that talks to the Docker daemon. And in this particular scenario, that will be a command line interface on a MacBook. But you could also use the API to have this controlled by the orchestrator. This is where the stuff really scales up. Now, where do these images live? Now, that's the registry and repository story. In the picture here, you'll see that there are a couple of registries which are sets of repositories, and each repository is like your set of images, and that's the core thing where the production environment or the user acceptance environment pulls the images from to create the containers. Now, here you can see that from a risk perspective, we have some components now that are an attack vector. If you want, here's where you could potentially introduce bad images into the whole story. And as containers and images are built on other images, you really want to think through how where that comes from. And we'll talk about that in the second part of this video. And there's also a public Docker hub. That is nice for experimenting, although for production you probably don't want to rely on that too much. Then the final complicated thing to discuss is Docker networking. In the same way as virtual machines, containers running on the same host will share networking hardware and networking code with the host that this runs on. And in fact, there's more sharing going on containers than it is on virtual machines. As I explained earlier, you even share the same IP address and all the ports that are associated with it, contrary to what happens with virtual machine. So the daemon, therefore, the Docker daemon, implements network functionality for the containers to communicate. And this is where a couple of access controls and other things are implemented. So it is part of the network. And you have to ask yourself, so what is the implication of this on a number of controls that you find relevant? Then a final thing to mention is that you can connect containers across multiple hosts and even across providers. And for that, you need some kind of overlay network technology. And that's actually a little bit beyond today's story here. Summarizing the Docker technology side and the Docker use case side, the whole point is that containers are a portable execution environment. The Docker daemon and the Docker client together have a much more standardized execution environment than a virtual machine gives you. The Docker daemon is the core where it all happens. There's less isolation between containers than between VMs. And the name of the game really is orchestration, which is much more native in the container and Docker space than it is in the virtual machine world.